So what I was just describing, there were some issues with the original ideas of how bonding occurred. We still understand that overlap between the electron orbitals, like in the atoms that are bonding, definitely still happens. But there's something funny that is going on within the atom itself that's bonding to make the bond better in a way. So right now, as this stands, this orbital is full. It's an s orbital, and it already has its 2 electrons. It has no reason to overlap and bond because it's full. There's no room for anyone else. Up here, again, this one is full, and same here. And then up here, yeah, there's space for someone else, like from another atom that could donate there or there. But the problem is that experimentally, that's not true at all. Experimentally, what happens is that this atom, this beryllium atom, he likes to form 2 bonds. 1, 2 bonds, not 0 bonds. 1, 2 bonds. And this atom likes to form 1, 2, 3 bonds, and this atom likes to form 1, 2, 3, 4, but he looks like he's only got space for 1. What's going on? So the only idea that everyone came up with, because they could tell that the atom's electrons counts don't change, and they said, well, something must happen in these 2 during bonding, not when it's sitting by itself. When it's by itself, it's fine. And it has the 2 electrons here in this s orbital, and it's happy. But when it goes to bond with something else, if it wants to bond, it's got to only have 1 electron in each spot. So somehow, one of these electrons gets moved up to here. So this is no longer here. And then if that happens, you can see like, there's room for someone else to come in and bond here and here. And then they're like, okay, so what happens here? So if we took this electron and took it away and we put them there, there would be room for someone else to go here, here, and here. And like, well, what does it work here? Yep, if we bumped him into that top space, there would be room for some other atom to bond in all those places. Well, that fits the experimental data of being able to form 3 bonds, with the orange, 2 bonds, and 4 bonds. But the problem is that this bond looks exactly the same as all of these bonds. So how can that be? And when we look at the bonds, they don't really look like P bonds exactly, and it doesn't really look like an S bond. What is going on with the bonds? So here's what we're saying happens. We're going to take these extra ones out. And it's like the atom, when it goes to bond, if it wants to have these 2 electrons bond, it's like it takes these and it merges them together and it averages them. That's kind of like what it does. It's weird. So originally you have this S and then you have this P. And remember I was saying, well, one of the electrons gets bumped up. So now you have an electron in each spot. But that's not enough. It does something else. It's like it gives each electron a really unusual kind of an area to be in. It's kind of like it takes half of each of them and sticks it together, and then it takes another half, like I'm kind of trying to do this right, but it takes the other halves and put them together. So the shape that kind of ends up looking like is that and that. Those are what happens when you hybridize, and this would be an sp hybridization, sp. So it's half s, half p, and then again half s and half p. So this might seem weird if you're stressing out right now and you're thinking, oh my goodness, how will I ever understand this? So this is for your understanding, only in the sense of, hey, this is out there. This is going to come back in organic chemistry. This is going to come back if you take other kinds of chemistries. As far as, are you going to be tested on it? You know what? We are not going to be giving you these shapes and saying, hey, can you tell us how all of these things hybridize all together? We're not doing that. We actually have a list so that you don't have to guess and figure out how they hybridize together.